So this is just an comparison at a given temperature, the differences in properties. There's a temperature regime where initially one is, the blue is the polyacetal, the red is the wax polymer binder. The main thing to note is you keep the powder concentration the same, but if you change the binder composition, right, your properties are going to be slightly different. The way you can make components is going to change a little bit, right? That's the main. And the equation that we saw allows you to describe that mathematically. Okay. And so you have a bunch of constants that are used in that equation that can be measured, and that becomes a material property. Okay, it describes a material. So now I know quantitatively these parameters change as I change the polymer, and so for a given system, that is a characteristic to pay attention to. How does volume change as a function of pressure and temperature? Right? In chemistry, we deal with PV equals to nRT, and then like you have Boyle's law and so on, right? And so similarly, you need to know that for the powder polymer mixture. Suppose you're molding something, right? You have a hot melt, it is going into a mold cavity under pressure, right? And it's beginning to cool down. For a given pressure, as the temperature reduces, right, the volume is going to change. If the volume changes, what happens? Right? Part is going to shrink. Right? So if the part shrinks more than it's supposed to, your dimensions are going to be off compared to what you want to predict. So that means in the process, you have to raise the pressure and add more material to compensate for the volume change. Right? So this set of properties, and this is called a Tate equation, which just says how does volume change as a function of pressure and temperature. It is a slightly more complicated version of an ideal gas law, just accounting for the fact that this is not an ideal gas, it's a powder polymer mixture, and so accordingly, how does volume change as a function of pressure and temperature. In the melt, right, the specific volume is higher, and in the solidified state, the specific volume is lower. Right? So makes sense, right? Lower the temperature, lower the specific volume. Right? Higher the pressure, lower the specific volume. Right? It captures those essences, similar to what might happen to an ideal gas. Right? Knowing this allows us to design the process for any given mixture as to how to change the pressure and temperature during the process so that the shrinkage of the material when it's cooling down is compensated for, and you can control the density of the molded part. Right? So this is why you need to know PVT properties for any given mixture. Obviously, here you can see the melting characteristics are different for this system compared to that. And so the transition region is quite different. You have a sharp transition here, and you only have a gradual transition over here. Right? Same thing, if you change the amount of powder, this is going to change as well to some extent. Right? More powder you have, the less compressible the material. Correct? Right? Polymers are more compressible than and then solvents are more, right? Right? Polymers are more compressible than powders, and so the greater the volume fraction, just like rheology changed, compressibility is going to change and shrinkage is going to change. From a process design perspective, as an engineer, you need to know how these properties are changing, how is shrinkage changing, how is density changing in the mold cavity, because you will get parts with different weights. And then if you remove the polymer, they're going to shrink to different extents, and you cannot control the precision. Right? So in addition to rheology, PVT is another property. And all this equation does is called a modified Tate equation, just like ideal gas law or the van der Waals equation. And mainly the relationships, when you expand them, end up having a lot more fitting parameters. Some of them are sensitive to changes in material composition more than others, but these fitting parameters then define the powder polymer system. Okay. Heat capacity, ability to store heat. The more powder you have, the less polymer you have. Polymer is what is going to store heat better. Polymers have a higher heat capacity than powders do, right? So solids have a lower heat capacity compared to liquids. There's less mobility in solids compared to of atoms compared to liquids, and so ability to store heat in different forms of energy is going to be lower. Right? Conductivity. You have more metal particles, you're going to have higher conductivity. The part is going to solidify more fast, right? More rapidly. So knowing the thermal conductivity of the mixture becomes important, and being able to model it as a function of concentration of powder becomes important, because then you know, just like viscosity variations give homogeneity, thermal conductivity variations or electrical conductivity variations will also give you a measure of homogeneity. What we do is, by taking advantage of those measurements, there are design software available that allow us to model, to input the rheological properties, the thermal properties, mechanical properties with process conditions, and for given shapes, tell, for predict how the process is going to work out for a given material. Let's see what this means. So let's see. So this is, if you click on this, these are the different interfaces on the software package called Moldflow. Okay, and you input all those constants over here that are for the cross model that relate viscosity as a function of shear rate and temperature. So instead of plotting all this data, you just need to put this model parameters. Alternatively, thermal properties, right? For instance, heat capacity is input in this manner. And you can see, in this case, it's specific heat, but you can also put in PVT properties. You can put other kinds of thermal properties, thermal conductivity. You can input over here, and so on. So if you measure these properties, model different kind of geometries. In this case, these are 50 micron feature spacings between the microchannels. They are made of alumina. And these kind of, we talked about briefly in the opening lecture 1 yesterday, that one aspect of my research involves making microsystems. In this case, they are microchannel devices made of alumina. So you injection mold alumina to create these kinds of spacings. Because alumina can withstand high temperatures and you can coat it with different catalysts, you can make high temperature reactors, for instance, right, and carry out certain kinds of reactions. They occur in much better yields in microchannel systems compared to others, right? So how do you make these kinds of microchannel systems? By measuring those properties of PVT, thermal conductivity, heat capacity, rheological properties, you can put that into the Moldflow software, and you can put in the information related to the geometry, and now you can begin to model how the material fills this mold cavity and how it solidifies after that. Okay. So for instance, right, you can see, can you see that if you just notice the regions of the channels, they begin to fill in last compared to the bulk, right? So towards, as the material is flowing for a particular time, it's going to lose heat, right? If it's losing heat, it's going to become more viscous. So more viscous materials are filling the very tiny channels, right? Higher the viscosity, more difficult it is to fill, right? lower the melt temperature and so more easy to solidify. So this indicates that you might have most of your defects in the microchannel region, the microfeatured region, because it is filling the latest in the mold cycle. When the melt temperature is the lowest and it's going to solidify very fast, and the viscosity is going to be too high to fill fast enough. Right? And so if you just take in the software, you can take a slice in different regions, and this is the region right near the surface, and you can see now very clearly that the regions closest to the channels, right, there's a delay and now they're filling up. See that? Right? So you can now, because of this intrinsic nature, you can imagine that there are going to be defects that occur during the filling. So the ground that I've covered so far in this class is, depending upon what you mix, you have to pay attention to how you mix. And then the mixture properties are going to be different. I've given you some examples of what mixture properties to measure and how to use it in design of a process. Right? So that has been so different types of applications of mixing. When do you mix? Right? What changes when you mix? Right? Different kinds of mixing devices. How to tell if the mixture is homogeneous or not. How to quantify it. How to measure different properties. And based on the variation of the properties, how to say, do you have a good mixture or you don't have a good mixture? Are the zirconia nanoparticles completely dispersed? Are they not dispersed? Right? How can I tell? Right? So we'll build from this information of basically focusing on materials to using these materials in different kinds of processes to create different kinds of shapes. So in tomorrow's lectures, what we will deal with are, first, what are different ways to create shapes using powders and polymers? And then we'll take a specific example and begin to see what is the relationship between material property, process condition, and geometry. One example that we saw was the design equation for mixing, right? We said if you change the particle size, you change the concentration of particles, you change the polymer, the mixing shear rate changes. What other design equations you can have if you go to different types of, right? So you had material and process effects. So in a similar manner, material, process, geometry effects, right? How can they be described in different processes? That's what we will cover after we take an overview of process methods, we will say what are ways to design processes.